code.
Yeah.
Okay, so now
Okay.
okay.
Yeah. You can just create a new template.
Okay. Microwave and RF, then periodic structure,
Periodic structures. Yeah.
and then
Unit cell. Yeah.
by the way, what is difference between full structure and this one, sir?
The thing is, unit cell structure and here actually it will apply the default applied flocket port. Full structure will apply different open boundary. That's it. That's the only difference. So these templates, no, yeah.
Please say it again, sir.
No. Actually, for unit cell, right, you will have a flocket port boundary condition. Means periodic boundary condition in this one. Okay. But full structure, no, you don't need to have. We already have periodic structure, right? So no, you can use open add space or something boundary like that.
Oh, I see. Okay.
Yeah.
Okay, now the next one.
Here, no, dispersion diagram, rectangular lattice. I think rectangular should be fine, actually. You want a dispersion diagram only, right? Correct?
Yeah, dispersion diagram and also, if possible, S parameter. Okay, let's see this one. Okay.
S parameter is, well known basically. So you can be able to.
Then eigenmode.
Yeah, it will come as eigenmode solver. Yes. You select dispersion, no, by default it will select eigenmode solver.
Oh, I see.
Okay. Yeah. But
Then,
if you use phase reflection diagram, then it will choose the frequency domain solver, basically.
okay.
Okay.
Oh, if I had selected phase reflection, then they would have given
It
me
will select.
option to select. Okay.
Yeah. Frequency domain and time domain. But you have to choose frequency domain only because this flocket board will work in frequency domain only. Okay.
Okay.
Yeah.
Cool.
This is the one.
Finish.
Phase one. Yeah.
First, let me save it. Okay. So
Okay. Yeah.
now we go to modeling.
Yeah. You can choose, for example, some patch itself. So you can use a dielectric resonator or anything. Anything, whatever you want, you can just select. Yeah.
Let's take it. I took cylinder, right?
Yeah. This is for the dielectric resonator you are talking about?
Yeah.
Okay.
Okay, so we have to give some radius. I do not know how much to give it.
Yeah. Dielectric resonator, I don't have any idea, but usually it will be lambda by 2, something like that, lambda g by 2, like that. Okay.
Outer radius is 0.
You want as hollow cylinder, or it's a full cylinder, right? Full cylinder you want, right?
Full cylinder, yes.
Okay. That's right.
And then Z means, let's say, minus.
That you can just give any dimension that you want.
Okay. And sir, material, which one should be better, sir?
You can select load materials, or you can define a new material also. It's fine. Okay, it's up to you to do that.
So if we define new materials, then
yeah, you go to PEC. No, here PEC, new material. You can define here, or you can define there also. It's fine. Okay,
so
anywhere you can do that. Yeah.
the new material, and then
Yeah, here no, you have to see, it's up to the material characteristics. For example, epsilon. So if mu is not equal to 1, then you have to feed the mu. And if you go to conductivity, if you go to conductivity, there is, you feed here some numbers, 1.2.2 like that. Okay. 2.1 like that. Okay. So then you go to conductivity. Here tan delta, you can just give. Okay. Or you see, whichever parameter is given in the data sheets, accordingly you have to feed here. For
Oh,
example, sometimes the reference represent electrical conductivity or a tan delta. So
mm,
tan delta is tan delta. They also call it as loss tangent, basically. Okay.
mm,
So
okay.
this defines the lossy is the material is that we can define. Okay, this will
Mm,
affect in the gain basically. Okay, okay.
okay.
Then yeah. So here actually we have to give exact value. So they usually see this dielectric material. No, they will measure it. For example, 2 to 18 gig. Okay,
Yeah.
and then they will represent one value at a time. Okay, for
Okay.
example, one value at a time. One
Mm,
value at a time. For example, so 2 to 18 gig, they will sweep the tan delta value and as well as the dielectric constant value. Then they will mention in the data sheet as, for example, 2.2 at 3 gigahertz, 2.2 at 10 gigahertz, like that. They used to mention in the
okay.
data sheet,
Okay.
which means, see, we have to see, for example, while choosing material, no, you have to see, okay, yeah, I am going to use this X and XYZ material. Okay, so we have to see how much is the variation in terms of dielectric constant when you work on the metamaterial or something like that. Dielectric constant is crucial there. Any antenna design it will be the crucial, but metamaterial it's a highly resonant structures, right?
Yeah.
So what happens is if you have can you give me control and can you open this one paint
Okay. I have given the control, sir, if you want.
paint basically. Can you open the paint and share it here? Ah, yeah. Yeah, yeah, I can see now. Okay, so usually the plots will be something like this. Okay,
Mm,
so
mm,
here it will be frequency.
yeah.
Okay, then
Mm,
here it will be epsilon or tan delta, basically
mm,
tan
okay.
delta. This is loss tangent. Okay, so
Mm,
here it will be, for example, see, it's they will measure it as 0 to 18, for example. Okay,
mm.
0 to 18. Then the value may be
Oh,
like
I
this.
see.
Okay.
Okay.
Okay, so but they will represent in the data sheet as, for example, 2.2 at 10 gig. Okay, 2.2 at 10 gig. Okay, basically.
Oh,
Okay,
okay.
2.2 at 10 gig. So which means, so 2.2 is the value applicable only for those frequencies. Okay, there will be a variation, plus minus something, plus minus. The tolerance also some data sheet will have, plus
Mm,
minus point 2, point 5, like that. Which means this dielectric constant no may, for example, may come from 1.8 to 2.8, like that. Okay, plus minus point 0.5 means 1.7 to 2.7, like that.
mm,
It will be
mm.
varying. Okay, so
Okay.
why we need to concern about this? It is because, see, epsilon r value, it's a kind of, for example, in layman language, if I say, see, the C is equal to square one divided by square root of mu naught epsilon naught, right?
Right.
Correct. Okay,
Mm,
but when this is applicable for the free space medium, correct?
right.
Okay, but when you have a medium, okay, any glass or something like that, okay, so what will happen is, so this medium, if epsilon, so the velocity will become like this. Formula will be 1 divided by square root of mu naught, epsilon r. Okay,
Yeah.
epsilon r. Okay, so this epsilon r, no, if you have too much variation, what will happen? The velocity also will vary, right? Phase
Right.
velocity. So see, these are all interlinked parameter. When ZR is epsilon r is changing, so what is happening to the velocity? Velocity is changing, right?
Mm,
Velocity changing means what? So the obviously the frequency is going to change, right? Slight drift in the frequency as well, right? Because frequencies also, for example, C lambda, right? Correct?
yeah. Yeah.
C lambda or C by
Um,
F? C by F, right? C by F is the lambda. So C is the F lambda. So C by F will be c by lambda, right? C by lambda, right? So when the velocity is changing, which means the frequency is going to change. Okay, so all are interlinked parameter. When epsilon r is changing means propagation inside the medium is going to change, correct? Okay,
Yes.
but so say you are designing some unit cell, for example, x to y frequency, or for example, x to y frequency. So you are designing for a particular frequency only, right? For example, so then how do you define the bandwidth? So you will define the bandwidth, right? Based on the S parameters or dispersion diagram or anything. So you will define this way because because your epsilon r is not stable. Some material will not have stable epsilon r properties. So that's why we are defining the bandwidth. Okay, where you are achieving this material. Okay, so coming to this point, like metamaterial, right? So when epsilon r changes, what will happen? You are what you are doing indirectly, you are changing the velocity as well, phase
Yeah.
velocity. Yeah, there is a phase velocity, and many parameters are there. You can just get to know that. So because those velocity, so when velocity changing means frequency changing. In other words, if I say in the layman language, okay, so frequency changing, phase velocity changing means frequency changing, which means see it may go like this.
Right. Right. Yeah.
Correct. It may go like this. Okay. So here indirectly what I'm changing? I'm changing the amplitude and phase as well. Correct. So how I am saying phase? Say for example, see this is the sine wave. Correct.
Okay.
So this is the sine wave, right? So this we call it as this is we call it as lambda, 1 lambda, okay, basically. So
Yeah.
this we call it as lambda by 4, which corresponds to 90 degree.
90
Correct.
degrees. Yeah.
Correct. Why we are saying 2 pi by lambda. Correct.
Yeah.
So then the KD, actually we used to call it as KD, yeah, KD like that. So D is lambda by 4. K is propagation constant, which is 2 pi by lambda. Lambda by 4, what will happen is lambda can cancel. The 4 will be pi by 2 will come. Okay. That's how this 4 by lambda by 4 means corresponds to 90 degree. Correct.
Okay.
So then the other point is will occur at this point, right? Lambda by 2. But here it is changing, keep on changing means what? So the indirectly what you are changing, you are changing the phase as well. Correct. Phase constant, propagation constant is changing, and the phase is changing, and also the phase velocity is changing. So everything is changing. Okay.
Right.
I think
Right.
you got the point, right? Because when
Yes.
epsilon are changing means so many parameters are interlinked parameters, right? So I see ultimately what I'm trying to say is one minute, let me delete this.
So
Let me delete.
we can extend it. Okay.
No issues. No issues. Okay. So ultimately, what I'm saying is, see, this is the material that you have. Okay. This is the material that you have. Okay. Okay. So when a wave propagate like this in a free space, it will be propagating with the velocity of c naught, which is 3 into 10 power 8. Correct.
Yeah.
Correct. The moment it enters, what will happen? Here it will see different dielectric constant, correct? Yes, so far it is seeing epsilon naught, mu naught, right?
Right.
The moment it enters the material, it will see epsilon naught,
Right.
correct? So what will happen is, so what is happening? So in the material, which is, altering the propagation of the waves. So inside the medium, so far it will be lambda naught. Why lambda naught? The wavelength will be lambda
Yes.
naught.
Yes.
Lambda naught will be C by F. Okay.
Yeah.
So the moment it enters to the medium, there will be a change in there will be, we will experience, the wave will experience changes, right? So these changes, how it happening? Like I said just now, right? When epsilon r changes, you will see the velocity changes. Velocity changes means what? Indirectly, what is changing? Frequency is changing, and
Yeah.
also phase, amplitude, everything is changing. Correct.
Yes.
So yeah, okay. So here, uh, we can see that see this material. Another point is like this material should be a homogeneous medium, non-homogeneous medium. Many material are there. Okay, so most of the time we use material as homogeneous. So we assume that it is a homogeneous, right? So the one full material is a homogeneous material substrate. Substrate that whatever we use is, which means what I'm trying to say is epsilon r and at some frequency. Okay, so some cases what will happen is, see, if it is in non-homogeneous, what will happen is epsilon r, see, at 10, if I, for example, 10 gigahertz, I am just measuring the epsilon r. I am cutting this piece and then measuring the epsilon r value. I am getting some value, for example, 2.2. Okay, so here I am cutting the piece and then measuring the epsilon r value, maybe 2.2205, like that. Okay, so if it is a light variation, it's fine, which means homogeneous. If it is, there is a, some material may have a, non-homogeneous property also. What will happen is, here I may have a 2.2, here I may have a 2.4, like that. Okay, so that also tricky part basically. So that accordingly the propagation also will change, and the over the material itself. So the propagation gets changed. For example, whatever behavior I'm getting here, I will not get here, right? So that way, this is how, this is the maybe a fundamental principle of metamaterial. How what we are doing is, see, so it is this case is for the plain material. Okay, plain material means plain substrate, which is having of epsilon r homogeneously. So it is having epsilon r throughout the medium. It is having this value. Okay. Next, this is one part. Another part is thickness. Thickness also play a big role. Okay, so you might have seen patch antenna formulas, right? So operating frequency, if you calculate, then you will see W by H and those values, right? Parameter, right? Epsilon are effective. Accordingly, only you will define the frequency of operation and other stuff, right? So what it does is thickness also play a major role. Okay, thickness and this epsilon r. Okay, these two parameters. So now you might have studied in the patch antenna theory that epsilon r effective. There is one parameter called epsilon r effective, which means effective dielectric constant. So effective dielectric constant means see, the in patch antenna how it arrived at is, for example, okay. So here patch antenna, no, see, we'll have a substrate like this. Then you have a ground plane. Then you have a patch. Correct? Okay. Now, so it is like you assume that it is for example, positive. This is negative. Okay. You assume that it is a positive. It is a negative. Okay. So if you supply voltage, no, there will be a current flow and other stuff will be there, okay, because it is having a resistive property. So the open circuit, this we call it as open circuit. So open circuit voltage will be high. The sine wave will be like this. Correct? Open circuit voltage will be high. So current, at that same time, open circuit current will be 0. So therefore, the current curve will be a half lambda, like this. So once a half sine wave, right? That is why we are always designing patch antenna with the lambda by 2.
Okay. Yeah.
Okay. Yeah. Okay. So this current distribution is this much. Okay. So that's why you will get a maximum radiation in this point, least radiation in this point. Okay, because you are having current as high over here. Okay. So this how function is, for example, let us say is that this is negative, negative, negative. This is positive, 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 like that. So the similarly opposite will be there, negative and positive, positive, positive. Here it will be negative, negative. Okay. So you know that, see, there is a valence band, conduction band, like that. So in circuits you might have studied, right? When you find a hole, it will try to fill, right? Okay. Correct? Electron will try to fill that hole.
Right.
That's how this will, fringing field, will start, coming up like this. Okay.
Yes.
Okay. So here, so these fringing fields, this is only causing the radiation in the patch antenna, basically. Not the current that is flowing within this conductor, it's causing a kind of magnetic field, but this fringing field is the one, because the this portion, no, this portion, no, it's not causing any. It's a kind of a ideal capacitor. How it will look like? You will have a conductor, then you will have a substrate, then you will have a capacitor. So capacitor is a storage device. What it does is, so this the it will be a balanced one. Correct?
Yeah.
So plus minus plus, it will be a balanced one. But if you are going beyond this, it will become an unbalanced one.
Right.
Okay.
Yeah.
Right. So here you can see that. So these fields, no, so until this, it will be confined fields. Okay, within this portion. The moment here it will see the, because you are extending, it will see this some kind of fringing field. This field is called as fringing fields. In patch antenna, these fields are only contributing
the radiation.
Yeah.
Okay.
This only causes the radiation, basically.
Yeah.
This okay. This only causes the radiation. Okay.
Yeah.
Okay. Sorry. Okay. So this only causes the radiation, basically. So now the point I want to make it is, like, for example, in patch antenna, formula you might have seen, epsilon r effective is equal to epsilon r plus 1 divided by 2. Plus 1 divided by 2 plus some value will be there. Some 1 plus w by h, like that. 1 by 2 like that will be there. All right. So why they are putting like this? Because these fields not only passing through this substrate, but also in the free space, right? Okay. So dielectric constant will not be equal to epsilon r. Okay.
Yeah. Okay.
So epsilon r effective will be epsilon r effective. Effective is always greater than 1, but less than epsilon r value of this substrate. Okay, because we are taking average between these two, right? Free space and this epsilon r value. Okay. So this epsilon r, okay, average. Now the point here is just 1 second, please. 1 second. Yeah. So the point here is, like, so that's why they make it as effective dielectric constant. And see, this will be applicable. This is a raw term, right? Because you are taking average. But the thing is, the wave is propagating within the substrate for a longer time, means the thickness is high. But whereas here it is very short, right? Very small thickness, right? Where it is interacting with the free space. So that's why they added this term 1 by W by H. It is heavily dependent on the width of the substrate and height of the substrate. So accordingly, this is a correction factor they have.
Right.
Okay.
Right. Okay.
Okay, epsilon r effective. Okay. Now, so why I'm saying all this thing is that, see, you can see that effective dielectric constant changing when you change the patch size, effective dielectric constant always going to change, right? Correct?
Okay.
Correct? Because you see the area that is interacting with the free space is going to change, correct? And for example, see, instead of small patch, if you have a ring, you are having some interaction here also, right? Fringing field will be in this area also, right? So that also you are going to change. So here, ultimately what you are doing is, see, in metamaterial, metasurface, ultimately what you are doing is, you are creating an artificial dielectric kind of environment. Okay, artificial dielectric kind of environment. So artificial dielectric, what you are making? So which means artificial dielectric means what I'm saying. So you are changing the epsilon r effective. You are modifying the epsilon r effective. You are playing with the epsilon r effective. So because substrate you cannot do much, correct? Substrate is fixed. For example, Rogers 5880 FR4 or anything. If FR4 means 4.3, if that is fixed, right? Throughout the medium. The only thing what you can play is the one that is printed on the above, the one that printed on the bottom. Correct? In the patch, you can play with anything, dimensions.
Yeah.
You can have a slots and anything. So ultimately, what you are doing, you are playing with the epsilon r effective.
Yeah.
Okay.
Okay.
So why? So the moment you play with the epsilon r effective, what will happen to the propagation when a wave hit on this one? What will happen to the propagation? The propagation will change. Ultimately, will change. Why? Because the velocity is going to change. In the velocity means frequency change. Frequency change means, in other words, you can call it as phase change, phase and amplitude change. So if you tell in terms of transmission line perspective, see, L is equal to j omega say XL reactance. It will be J omega, sorry, J omega L, right? Okay. J omega L, okay. Okay. So the omega is what? Frequency, right?
Yeah.
Correct? So when a frequency changes, omega will also include this one also, right? Epsilon r value also, right? So when the moment you change the effective dielectric constant, you are going to change L and C as well.
Right. Right. Yeah.
Okay. So therefore, in other words, it is frequency changing, or in other words, what you are changing? Amplitude and phase. Because, in a layman language, if you see, the frequency changing means it will be like this, right? So amplitude and phase is getting changed. So that's how this, concepts arrive. So the moment you start playing with your, structures and, the structures, you will see that, effective dielectric constants are getting changed. Then ultimately, frequency is changing, and phase and amplitude is changing, LNC is changing. So many parameters are that. Okay.
So just a second, I will. Why it is showing meeting ends in 10 minutes? So I want to cancel it.
Okay.
Okay. So sir, if this meeting disconnects, then we will connect again, right?
Yeah. No problem. No problem.
Okay. So okay. So now I understood how everything is connected with each other. Yeah. So if the permittivity and conductivity frequency, that's why you are saying that if we give some value, then the for example, if we give this epsilon, then this depends on the frequency, the range of the frequency. Now I understand these things.
Correct. So range of frequency is very important,
Mm.
and changes, because so the why I'm saying here, see why I took this much time to explain you that epsilon r, how epsilon r is critical. See, see, you are designing for some X frequency. You are claiming that this will work for 2 to 3 gigahertz. How it will work? You have to design, see, your structure such a way that it will accept for wider bandwidth, right? Why it is cannot be have a wider bandwidth? Because the problem is, see, when you have a, the moment it goes away from the, when you have a epsilon variation, a huge, okay, but traditionally normal material will not have that much difference basically. So if you have a huge difference, then what will happen is ultimately your frequency of operation getting changed. So the many linked parameters getting changed, right? So that's why, for an exercise, you can do one exercise. For example, you can design a patch, or design such, just put some dielectric resonator, and then you keep on changing the dielectric constant. You will see the difference in the the frequency of operation, and as well as the other parameters, right? So that will validate you that, okay, yeah, there is a big play, is that right? So that's how it works. And also thickness also will play some role, right, in a wider bandwidth, because you might have studied, right? Thicker substrate will give you wider bandwidth, thinner substrate will give you narrow bandwidth, like that, right? Okay. So why? Because see, thicker substrate has a, so the last tangent how they calculate is with the free electrons. That is affect basically in the substrate. Basically, substrate is not an ideal substrate. Ideal substrate means, ideal dielectric means what it have. It will should have a zero conductivity, right? Okay.
Yeah.
But it will have a certain conductivity. That is, how much free electrons you are finding. Based on that only, this the tan delta is calculated. Okay. So this we call it a, see, according to the dielectric, it is a loss, right? It should not, it should be a kind of insulator, but it is not behaving as insulator to certain extent, small extent, right? It is a conducting also. So that's how that this tan delta defines. If you have a too much lossy substrate, then you will have a so many so many frequencies can be operating. So that's why there is a substrate thumb rule, like it's a normal thumb rule. Okay, not not necessary for all the patch antennas, some all the cases, but some thumb rule says that if you have a too much lossy, then you will have a bandwidth, higher bandwidth. If you have a thicker substrate, you will also have a higher bandwidth. Why? Because see, Q and the bandwidth are inversely proportional, right? Q, quality factor. So when you have a low quality, when you have a lossy material, then you will have a low quality factor. Thereby you will achieve the higher bandwidth. So all these parameter will boils down to this concept only. So this is the maybe see it's according to me. Okay, maybe there is a more theory available. Okay, I am just saying in layman perspective. This is the for the foundation for the. So now you could get a picture, right? You
Yeah.
can talk of metamaterial. You can talk of metasurface. You can talk of anything that you want. Correct. Okay, metamaterial, 3D metamaterial, 2D metamaterial, anything you want. What you are ultimately doing, you are playing with the effective dielectric constant. Thereby, you are modifying the propagation of the waves. Either you can absorb the waves, for example, it can act as an absorber, or it can absorbment means what will happen. So what you are doing indirectly, you are playing with the L and C, so that it will become resonance there. So that will trap the field, confine the field within the substrate, means within the structure basically. So that's why. And that is a kind of absorber, metametal absorber, like metasurface absorber. Many papers are appearing. And if you talk in terms of, for example, transmit array or sorry, reflecting properties or transmitting properties. So ultimately, what you're doing is beam steering, whatever you want to do. So ultimately, what you're doing, you are playing with the Fi epsilon or effective, thereby the frequency or amplitude and phase, and also the LNC. So all these parameters are getting affected. Therefore, what you are doing, you can play with the wave that is propagating inside, within the that structure. So you can control the beam as well. Okay. So all boils down to that only. Yeah.
Okay. So by changing the physical appearance of a patch or dielectric rod,
Exactly.
we can affect
Exactly.
activity, and that means we are affecting the L and C. So
Yeah.
that means we are changing the behavior, like we are changing the resonance behavior of that structure, and
Yes.
it may act like a absorber or reflector. Okay, perfect. Now I understand.
Anything. Yeah. 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 Exactly.
Okay, thank you. So, sir,
Correct.
I think in 2 minutes it will disconnect. So I'm disconnecting it and I'm connecting again, right?
Yeah. 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 No problem. The same link or
Yeah.
what?
Um, Maybe at I sent the second link, so I'm clicking on second link.
Yeah. Yeah. 7 p.m. link. Okay.
My
Yeah.
email, I sent also a second link from 3:30 to, sorry, 7 p.m. to 7:30. So please click on that.
Yeah. Yeah. Yeah.
Okay.
Yeah. Yeah. Yeah.
So
Okay. Thank you. Okay.